because I can't stand at all. So yeah, so I work with investors all the time. Because that's what I mean.
Woo! Okay. It was church yesterday. Great. So good.
Ours church has no heat right now.
No heat. It feels like it's moving.
They said there's certain people that come and turn the boiler on. It's like an old building. And they say sometimes they don't keep up the temperature. Okay. So like they gotta come around. So I don't know what area.
So if it has a boiler, does it have those? Is it radiant heating of water that runs around?
No, I don't know. Probably. They said it's quite the process. Wow.
Cold. It is getting cold. I have to blow the air through my sprinkler systems, right? You don't blow out your sprinklers, they're gonna freeze. So I need to prevent that. Okay, well, good to see you here today. Let's get started. How about Cindy? Could you offer us a prayer to get us going?
Yes. Dear precious Heavenly Father, we are grateful for this day, opportunity that we have to be able to meet us. We're grateful for the preparation that Brother Smith has done for us, and we're grateful for everybody that makes this possible. We love you, Father, and we please ask you to let's see what we'll be able to understand the material today, and we'll be able to do all the stuff that we have to do this week. Please, Father, help those people who are struggling today, and please send the love that and the spirit of comfort that we'll need. We love you, Father, and say the same name, by Son Jesus Christ. Amen.
Amen. Thank you. I appreciate that prayer. It goes along with this quote right here from Elder Maxwell. A long time ago, when he was speaking to the singles ward at state conference, he says, "Please consider the bearing capacity." We could just stop right there. An apostle said the word bearing capacity. I love that. You should go search. Find any others. Go hunt. I would love for you to send me an email if you find a quote from a leader who talks about soil mechanics in their quote. This is awesome. Please consider the bearing capacity of others traveling the straight and narrow way. Most of us are so concerned with our own needs that we scarcely notice the needs of those around us. We all have a certain amount of capacity we can hold up, and sometimes we fail, right? The load gets so much, we just burn out. It gets hard. It's tough. It happens in school. We just get, there's tough times. All of us have difficult things going on, and we're very concerned with ourselves, but be considerate of others, pray for others. I appreciate that prayer, Cindy, praying for others. Okay, so let's start with some questions today before we go. And I heard through the grapevine that there this is a rare, if it ever happens, it's rare. The book has a mistake in it. Is that what I heard? Is this true? Could this really be? I don't know. So we do problem 5 or 5:16 together. Is that the one that have the 7:13? What chapter are we in?
7:16 or 5:16.
5:16. Okay, 5:16. That was the one where we had that influence method where you had to have fun drawing little triangles and rectangles. You do that one together. Anyone? That's going to be due tonight. Midnight. We still have some time, but we can do it together as a class. I had a student come in earlier today and they asked some questions about that one. I was stumped. I was like, not until after it's left, I looked at it again. I know what's going on. And yes, the book does have mistakes. So let's go over that one. So if you have your book, let's just turn to homework 5:16. It tells us that we have a continuous foundation. And let me pull up some equations that we're going to see. Let me pull up a different lecture from last time. Let's see, elastic settlement. We were talking about this method right here. Just look familiar. This is what our problem's all about. It gives us this equation, and it says, and so we need to figure out. We say we have a continuous footing, and we need to figure out how much it settles. Our equation that we're going to use is at the top, and we need to figure out all these things. Now, I think we can just start with the low-hanging fruit. the easiest values to grab are these C1 and C2s right after that. And they're given to us right here. The only thing we need to understand is what's the difference between Q and that Q with a little dash on it. What's those differences right there? Who wants to teach? What do we got? What's the difference? Q and then this little Q dash. Where's the difference?
Oh, Q dash is your effective minus your load, right?
Q dash.
Load of the footings.
Okay, so in our problem, what is our Q dash? Okay, perfect. So we have little q and equals 195. All right, does everyone feel good about that? Okay, so we do need that for this C1 right here. But what about the top, the numerator? What's Q? What's Q? Effective stress at the base of the foundation. So how do we calculate that again? We need to get this Q now. It's effective stress. It's the unit weight times the depth. So what's our unit weight of our soil? 18. Okay. So, and then how deep are we down to the base of the footing? Is that what it says right here? The base of the foundation. 5? 1.1. 1.5. Okay. So what will this equal then? 27. 27. Okay. So we can knock out C1. Now we have everything we put down there. What do we get for C1? Yeah.
0.919.
Okay, 0.91. Perfect. Feeling good about this. Let's do C2 now. Years. How many years do we have? In the problem it says we have how many years? 10 years. Okay, so if you put in a 10, C2, when T equals 10, what do we get for C2? 1.4. 1.4. Okay, so far we're cooking. Yeah. We're trying to find settlement again. That's the whole point. We know the first four, C1, C2, Q dash, and Q. Now, what is this funny thing now? This is the hardest part. In order to sum up your influence factors, which is the IZ, divided by your stiffnesses, your modulus of elasticity, that E, multiplied by the layer thickness, that's going to require us to draw two pictures and do some interpolating. That's the hardest part of this problem. Having confidence that you're interpolating correctly. So we need to draw a picture that looks like this in order to figure out this last little bit right here. So there's 3 points on this plot right here. And now there's two different charts. And every problem we do, we use one or the other. How do we know which one to use? And each one has some different meanings in it. Each one has a Z1, it has a Z2, and an IZ max. Those are very important. We have to know all of these Z1s and Z2s and IZ maxes to figure out the rest of our equation right here. So first we have to decide which one to use, right? Because if I use this one, Z2 is equal to 4B. But if I use this one, notice Z2 is equal to 2B. I got to make sure I choose the right one. And notice up at the top, Z1 is equal to 0.5B, whereas Z1 is equal to B on this one. So step one, which one do we have? What are the differences between these two?
Continuous or...
Ooh, okay. The key is right here. You use this plot if your length over base ratio is greater than 10. Length over base. What's our base?
2.5.
Okay, our base is 2.5 and it's a continuous footing and the length is just infinity. It goes on forever. So infinity divided by base is definitely greater than 10. This is our chart right here. So some givens now that we've determined any questions so far? This is important. A lot of students, we don't know which chart to use, and the charts have definitions of 3 variables that we're about to use. So now we know that Z2 is going to equal 4B because we're using that chart, because we know our length over base ratio is greater than 10. We know that Z1 is equal to B, and we know that Imax, I don't really know anything more about Imax. Okay, so, we do know where it starts at 0 though. Notice if we chose this chart, the Z at 0, I is equal to 0.1. What is I equal to on this one? That's important to know. It's at 0.2. So we'll call that the influence factor at 0 is going to equal 0.2, only because we chose that chart. That's what it is. Okay, so the next step is to draw our pictures. So, yeah.
Do those equations trump this graph? So say if
that's a good
IZ
question.
was like, it ended up being 0.1, that would be instead of 0.2?
If you want to get more precise, yeah, you can go here, but this is kind of just saying, if you have a big length, like we have a continuous footing, what if you just put in 100 right here, divided by 2.5, that'd be like 40 minus 1, it'd be like 39. I'm just making up numbers using a really big L, like we're using this one. If we had a really big, like 39 times 0.11, that would be 0.3, that would be bigger than 0.2. So this kind of caps you at 0.2. So I guess if you want to get a value in between 0.2 and 0.1, then you can use a little more granular. But here we just say IZ at 0 is going to be, equal to 0.2 if you have a good, really long footing. But if your footing gets shorter, at some point, then yeah, it's going to be somewhere in between 0.1. That's good, yeah, because these charts aren't clear and there's a lot of scratching your head. That's why I always recommend when you're doing this class, you're doing the homework, that you just work in groups and you ask these questions like, how do you know that? Because it doesn't say that anywhere. It doesn't say use 0.2. It just gives you a plot and there's a 0.2 on there and you're like, do I always use 0.2? What about this equation? Anyway, you're safe to use 0.2 in this case. Okay, so far, we've kind of figured out some of our variables, but now the hard part begins, making a little picture. I don't have a very good picture to use. Let's see. But we need to make something that looks like this. This is not your example, but we need to draw a picture and we need to kind of draw two side by side. The book gives us this picture right here, right? There's 3 different zones in the picture that's given to us. And then next to that, we need to draw the picture that the book gives us. And then right off to the side of that, we need to draw this little triangle. The triangle that starts at 0.2 up the top right there. And then we need to calculate this point, because then we'll just draw a straight line down to it. We need to calculate what its depth is. What is Z1? We just found out, we told ourselves Z1 is going to equal B. So what is B? In this problem in the homework, I think the homework said it was 2.5. So we're going to draw a little triangle that starts at 0.2, and it's going to go to some maximum influence value, and it's going to occur at 2.5. That's what we know so far. And then from that point, that maximum value, which we haven't calculated yet, it's going to go in a straight line down to Z2 where there's no more influence, meaning the soil doesn't feel the weight of this footing anymore, and it's going to happen and occur at Z2, which we now know because we chose the chart, it's going to equal 10, right? 4 times that base. So we kind of know some points on the chart. We know where it's going to terminate at the depth. We know where it's going to start at. We don't know this. How do we calculate this I max value? And I think that was given to us right here. It doesn't really say it clearly, but I max, IZM, M stands for max. It's going to equal 0.5 plus 0.1, and then it's going to use some of these Q's right here. But then it throws this weird value at us right here, Q prime Z1, whatever that means. Hopefully we have an equation for that somewhere. So to find the max, let's just do that equation really quick. I think this is where things start to kind of get squirrely. IZM equals, what do we got? We have some values that we already know. We can do 0.5 plus 0.1. This is, then we know some of these values, right? We know, what is that? Q, the big Q prime, what's that value going to be? 195. And then we're going to subtract what from it? 27, which we figure out over there. Then what goes down here? And that's where the big question is, right? That's where the book maybe has an error. It does. It's a mistake. QZ1. It's not defined on this page. I think we have to go to our textbook to figure this out. Let's see if we can figure this out. What page would it be on? I think this equation 258. Okay, 258. Where is it? 258. Oh, there's at the bottom. It says QZ prime 1 equals, it's at the very bottom of page 258. It says it equals the effective stress at a depth of Z1 before construction of the foundation. So, I mean, here's our soil right here, the top of the ground level right here. We're going to be digging a hole, and then we're going to be putting a foundation on it right here, right? And it's telling us that the value we put right there is equal to the effective stress added depth of Z1. So it's saying what's the effective stress at Z1, which equals B, which is at 2.5. So it'll be the effective stress, which we can find that by multiplying this unit weight times 2.5. What do we get for that value? 45. Oh, but is that all? Because we just calculated Z1, and we probably should put some plots on here. Where is Z1 on this plot? You go from the top down, is that Z1, or you go from down here? What's Z1? This one right here. So this is Z1. So Z1, we calculated that, and that's going to be at 2.5 feet right here. So we'll take the unit weight, multiply it by its depth, but we have to also add this material in as well. So actually, we need to be careful. So this value that we put right here, it's going to equal that 18, because that's the unit weight of our soil, and it's going to be this depth, Z1, which we know is 2.5, plus this depth right here, because we know it says a little note right here, before construction of the foundation. So it's asking us, and so what is this called? What's another name for this depth right here?
DF.
Yeah, we call that DF, and in this case, it equals 1.5, right? Okay, I think that the book put in 2.5 right here. And so the book says this is 5, but we know it's wrong. And so we put in a 1.5, so it's going to be a 4. So our value is going to be slightly different for the max in the book got. Not a lot, but it'll be a little bit different. So good catch on those that figured this out. So sorry about that. It was frustrating. I should have told you that before, but I think this is the part that we got wrong. So now we can draw this little diagram correctly, right? We know that this value, if I work this all out, what does this equal? Like 0.65 something, right? Yeah. So 0.65. That's just telling you what this max peak is right here. And then this is where the fun gets. We know we have a layer of soil, and it's pretty stiff for the first 2 feet, and it gets really stiff. I can't remember all the deals, but in order to calculate this layer right here, I think this layer goes down to, it's 2 meters thick, and then it just keeps going down. But there's like a little half meter right here where it's still not a maximum yet, but it's into this new material that has an E of 12. And I think this has an E of 6,000, right? I know I'm just going fast, but this is where I think this is the hardest part right here. And once I just go over this, I think you'll be able to do the problem for the rest of the way. Because what it's going to require us to do is to break the soil layer that we've been given into different zones. We'll need a zone 1 here for the first 2 meters. Then we'll need a little zone right here because it's still not maxed out for the first half meter into this new material. So we got a zone 2 right here. Then we have a zone 3 where it's hit the max and now it's coming down. And then I think that E changes, right? We have some different value of E, right? Just remembering. So we have 4 different zones. So we would need a table that would have 4 different rows on it. And the table would look something like the columns. The first column would be like the depth. And this is shown in the examples. Then we have what is the thickness of that layer, the change in Z, what is the stiffness, and then this is the hardest part. What is IZ? Right, so we can calculate these values pretty easily, just plucking that E's off of here, the thickness is off of there, stuff like that. But how do you calculate Z at these different set depths? This influence factor. We're able to figure out its maximum value using this equation. Go ahead.
To the right side of the square, the rectangle you made, is it where it intercepts that? Like if you draw a line from 2 meters on the y-axis.
If I went 2 meters over right here.
Is that what it is?
That's IC.
Yeah, this is right. That's going to be IZ. Yeah, there's a multiple IZs. I mean, this is I when it's 0. This is I when it's max. This would be called I when it's at 2 meters. There's an I somewhere in the middle of this layer. There's another I here. There's I's everywhere, right? There's an I at every depth Z that we possibly have. And so our goal is to figure out what is the I at the middle of each of these 4 zones. So we want to know what the I is about right here, right? It starts at 0.2 and it goes to 0.65. I don't know. I don't just need to know where it starts, maxes out, and then ends down here at 0. I want to know the I value at the middle of each of these zones that I have. So I'm gonna have to find an I value here, and the I value in the middle of this zone right here. Then I need to find the I value somewhere in the middle of zone 3. I'm just gonna say the middle of that, somewhere right here, and then somewhere in the middle of zone 4. That's what we're hunting for right here. And that just takes some interpolation, right? There's not an equation to figure that out. We just have to know that over this depth of 2.5 meters, it went from 0.2 to 0.65. We have to kind of figure out what that ratio is, and then say, okay, so if we went down 1 meter in this layer, how far would it go over right here? And I think for every meter that you go down, if you just did the math and look at the slope, it changes by like 0.18. And so you'd have something like that. And so to get this zone right here, it's like 0.38 because you go down a meter to the middle of this zone. Is that making sense? I know I just kind of softly put it together, but that's the idea. And we're hunting for these intermediate little zones right here. And no, there's not a quick equation. You just have to do some interpolating to find these values. And then you'd want to interpolate in between. You go down 2 meters, what's this value right here? And maybe it's like 0.53 or something like that. And this is 0.65, so where would that middle be? Maybe 0.59 or something like that. I think that's kind of what you're just gonna have to interpolate. So your answers might not perfectly match the book, but you'll be close enough to get self-confidence about what you're trying to do. The ultimate goal is to recognize that a footing in soil influences the ground differently. And so the whole point here is we're trying to figure out settlement with considering the fact that the soil doesn't all feel the same weight at all these different depths. It feels less and less weight the deeper that you go. So anyway, this is just one of the many. So don't get hung up on it because there's so many other ways as well. But this is in general what you do. Yeah.
So what are those like bottom to 3 equations where it's like I sub z and it has like z1 over b? Like we didn't use any of those.
We didn't because the problem that we were given gave us these values right here. But what if you weren't given those values? What if maybe instead, when you did your soils exploration, you rented one of these CPT rigs, these cone penetration testing rigs. They spit out values of resistance and stiffness in a form that's called QC, the cone penetration resistance. And you can correlate that to this E, the modulus, by this equation. So anyway, those weren't needed. It's giving you extra information to handle multiple scenarios.
But those other IZ equations, it's like the one with less than 0.2, that's if we do have a length and a base.
Yeah, we just ignored this and said, hey, we're using this guy. Yeah. But yeah, if you did have somewhere in between, that would be a good one to use.
And the other 2 at the bottom left, did you ignore those as well?
These ones? Yeah.
I didn't know those were for at all.
Yeah.
We didn't have, no, we did.
That just tells you
We didn't need those because again, we used just the charts right here. Yeah. We just plucked it off the charts. I mean, essentially it's how they got those values right there. But yeah, we didn't need those in this case. You're right. So this kind of information overload type of a problem. And the skill was discerning what parts of it you needed and what you didn't. I've never having seen it. Yeah, there's lots there. You're asking the right questions. So I know that was kind of quick, but the book did have an error, so I wanted to take the time to go over it. Because I think you have confidence. You do know what you're doing, even though the book threw you a curveball. Any other questions about that one? That was a good one. And the others, they were way more straightforward. We just used the N value, the flow counts, and estimated settlement. So far, we talked about bearing capacity of soils, many different types of conditions of soils, interlayered soils, stiff soils over hard soils. Throw a water table in there, put it on a slope. We talked about slope safety and factors of safety on different slopes. We talked about now settlement. There's many different ways to do settlement. And so today we're shifting gears. We're moving to a totally different topic. And we're going to talk more for the rest of the class. Really, we're kind of done talking about settlement and bearing capacity. Now we want to start designing foundations, right? This class is about designing foundations. But before you can design a foundation, we had to first understand that most soil fails either in two ways. Either has too much settlement or that there's not enough bearing capacity. So you'll have this shear failure, building will tip over. And now that we know how buildings fail, let's learn how to design walls and piles and different kinds of foundations. That's where we want to go. So we're going to start, and we're going to go pretty quick for the rest of the semester. We're going to spend 2 days probably on each of these different ways of designing walls and foundations and piles and drilled shafts. And then we'll round up the semester talking about ground improvement. So you roll up onto a site and it just has terrible conditions. How do you improve the ground? That's where we're kind of headed in this course. And so this course is very fast paced. We don't get deep into all of these chapters. Each of these chapters, you could take a structural engineering class on how to do all the design work and stuff, but we just skip that. What we cover though is definitely enough for the FE exam and the PE exam. If you have a question about settlement, you probably will see a lot of these. I should pull up the PDF, the technical portion that you can use. You have all the equations for the FE exam on that packet. I'll make that available to us at some point. But hopefully some of these will start. You'll see these and they'll be familiar. That's the whole point. If you ever have a quiz or test question, you want to be able to recognize, oh yeah, I've seen this kind of before. I recognize some of the factors. Let's try iClicker though. I want to make sure we have iClicker accessibility. So log in. This class is under 441. Let's just see if we have iClicker available. I do have a few, but I just want to see kind of where our level of understanding is, really how much we remember from 341 as we talk about a new topic today. Chapter 6, mat foundations. Mat foundations. That's where we're headed. And while you're loading up iClicker, oh, you're fast. I got 15 responses. I do want to read the introduction to mat foundations. It says, under normal conditions, square and rectangular footings, such as those described in chapters 3 and 4, are economical for supporting columns and walls. However, under certain circumstances, it may be desirable to construct a footing that supports a line of 2 or more columns. These footings are referred to as combined footings. When more than one line of columns is supported by a concrete slab, it's called a mat foundation. That's kind of where we're going today. Yeah, no. Nice. Okay, so today we're going to slow it down on the number of equations that we're spitting out today. We'll probably only have 3 new equations, and they're going to be very familiar. So in chapter 3 and 4 of this semester, that's where we first started talking about bearing capacity. That's when Terzaghi came in, our hero, and told us the equation to use. We're going back to that old equation. And so it should be familiar to you. But we're talking about not just a footing. What if you have a building that has such high loads on it that you need to put a lot of columns and space them really close together? I mean, each column would maybe require a big footing, like 10 foot by 10 foot or something like that. But what if those footings are now so big they start overlapping each other and things like that? We need to consider just making one giant foundation where those column loads go into one continuous mat foundation. That's what we're talking about right here. So ignore this. I'm just talking about the concept of this foundation type where you've got one continuous foundation supporting. No more strip footings, right, that you see on residential homes and stuff going around a home's wall. I'm talking about strip footings or just square or circular footings anymore. We want to talk about how do you determine the bearing capacity for something with a combined footing or a mat foundation, also known as a raft foundation. So question, does the ultimate bearing capacity typically go up or down when using a mat foundation? What do you think? Is that the idea of using a mat foundation? Does that help you or does that hurt you for ultimate bearing capacity? What do you think? Let's give out 2 responses. Well, another iClicker question. We'll have maybe 3 or 4 of these today. I just want to see what you think. And the only way you'd know this is maybe through the reading or something like that, or watching the video before class. What do you think? Ultimate bearing
capacity of the soil.
Yeah, so up or down. Well, not so, just like the overall, I guess the gross. Maybe I should put gross. Yeah. All right, good job. There's 19 responses, 20, even better. Okay, it goes up. It does go up. That's perfect, right? You have more ability to hold load because you're making a bigger and a bigger and a bigger footing. There are some things to worry about. We did hint before that if you start packing two footings closer and closer together, their zones of influence do intersect. And at some point when you get two of them really close together, they intersect so much that you actually just design it as one. So when you have two footings, and this one can hold like 2,000 pounds, this one can hold 2,000 pounds. As you get closer and closer together, yes, they can both combined hold 4,000, but at some point they intersect too much and they influence each other. And so they can't hold 4,000, maybe it's a little bit less. But then there's some place kind of where there's a sweet spot and you end up just, instead of just having two footings, let's just design one big one and that can ultimately hold more. Let's just say 5,000. I'm just throwing average numbers out there, but just there's a game that we have to play. And so now we're just going to consider the fact that we have one big footing. And let's look at some pictures. Let's see what that even looks like. This is a beautiful picture right here of a giant footing. It's like the whole city block is a one big slab right here, right? That's huge. Let's turn the lights on and enjoy this picture. That is a sweet. If you ever get a chance to be on site when things like this are happening, you can just be like, yes, I'm so glad I'm a civil engineer. I've never been, I don't know where this is, probably some big city. But some quick observations. First of all, that's massive. And you can see in the background, there's some really big buildings in this vicinity as well. Second of all, look how neat those walls are. I mean, they dug down, what is that, 40 feet maybe? They shotcreted the walls, they embedded it with soil nails and they anchored them in. You can kind of see each of those little, each one of these is a big steel rod that anchors in, similar to the anchors, if you remember that video that they're doing under the temple reconstruction. They're anchoring and essentially bolting all the granite foundation blocks of the Salt Lake City temple together. Similarly, they're drilling deep back in there at 20, 30, 40 feet so that it can hold up this wall. That's cool. That's a mat foundation. Look how many pump trucks are in there. 1, 2, 3, 4. There's like 5 pump trucks or more, all pumping the concrete. It has to all go at the same time, right? You can't start pouring concrete in this corner, have it harden, and then pour next to it. Otherwise, you're getting all these cold joints that put weak planes in there, and that's where it would crack. So the concrete all has to be wet, vibrated together, all as one, cure as one. And these are where all the columns would be tied down into the mat foundation. That's a cool picture.
Smith,
yeah.
When there's big buildings like that, like say like you have a smaller building and then like just a little bit away you have a huge building, is that zone of influence, like you're saying, like can you still say that same thing with the columns, like when you're moving them closer and closer together? If there's a big building next to my little building, is that going to affect the soil where I am, even though I didn't plan for that building there?
It totally can. Yeah, if you're saying that you have something this happens all the time in big cities, but the good news is, so here's your ground level right here, and maybe you have like a little house right here, and then you put a big building next to it. Is that what you're talking about? Could this zone of influence affect this guy and this one starts settling?
Yeah.
You bet it can. Typically though, what happens with the big building, it requires such a big foundation, and it's not a shallow foundation that it requires. This little building would have a shallow foundation, so let's just draw its footing right there. This big building would maybe be supported on piles or something that are essentially putting their weight on this soil. And so this is where the zone of influence would be. The bowls would kind of start right here. And so this building actually wouldn't fill, the little one wouldn't fill the big one because the big one doesn't start swishing the soil until this direction, because it uses pile to transfer the load from the surface and start contacting the soil at this point right here. And so this case, it would be safe. Where you have the problem though is before you put all these piles in, before you build the building, sometimes they dig out this whole area. And so this is now missing. And so now you have to worry about the side failing on the side of this building. And that's why you have to anchor these. These are just huge walls right here, like in this picture right here. And then there's these soil nails that come in at an angle, and they just pin and hold this wall in place. So the weight of this little building doesn't slide and cause a failure inside that hole right there. So yeah, usually big buildings, don't influence little buildings. But what if you put another big building right here? This big building then could have influenced the soil down here, right? So if we put another big building right here, and it has piles or whatever, then it has zones of influence. And now, yeah, we definitely have to worry about that. So, and maybe our footings have to be driven even deeper so they don't influence this one, but you have to definitely take the buildings next to each other into consideration. Yeah, it's crazy. And it's not crazy. It's just, you just have to take more things into consideration. So this footing right here, this is actually project the Hyatt that happened in Salt Lake a couple years back. And again, another MAP foundation, same picture, different angle. Look at all these pump trucks. 1, 2, 3, 4 pump trucks going in. This was a project, lots and lots of concrete, huge MAP foundation. This took a lot of, I mean, if you guys like testing concrete, this would be a wonderland.
So here's what I was kind of wondering, what kind of approach do they, crew towers in New York?
Oh yeah.
They're so massive.
Those are usually drilled shafts, and we'll talk about those in a little bit. And but drilled shafts are just like giant piles, but instead of driving the pile in the ground, you actually just auger out this big hole, 5 foot diameter, 10 foot diameter, go down 100, 200 feet, whatever it is, put a giant rebar cage in there, backfill with concrete. So then you have this giant concrete pillar, lots of them holding up the Twin Towers or something like that. Yeah, and it's expensive and it's massive. And it's exciting to be a part of big projects like that. So I hope all of you get a chance to be involved with some big project, whether you could be the concrete truck driver, the technician, the guy in the field. I don't care what part you play. These are just cool projects to be involved with. I love projects like this. So 20 years from now, if you're just not getting out in the field enough, volunteer to be a concrete truck driver. You can see some cool things to do. Let me tell you about this project though. It was big. It was a MAP foundation. Oakland was the team, the contractor who did it. I think there should have been an A in there. O-A-K land. Concrete team was pouring 7,000 cubic yards. MAP foundation, Hyatt Regency, Salt Lake City. So it's standing there right now. It's doing good. 26 stories tall. Pour began Friday night at 5 p.m. and was completed 6:30 a.m. Saturday morning. So 13 and a half hours, 2.4 million pounds of rebar. You can see those MAP foundations, lots of concrete. I mean, steel in them. 6 pump trucks, 5 batch plants, 800 concrete trucks, 2 shifts with 95 drivers, 95 concrete carpenters, finishers, labor. Lots going on. So if you were a concrete technician, you were probably standing, each pump truck probably had a technician at it, and they were probably sampling maybe every 4th truck or something like that. And they were probably pouring as fast as they could. So by the end of the day, I mean, how many sets of cylinders would that be? 7,000 cubic yards. If you're testing even every 100 cubic yards, that's 74 different sets of concrete that you would have by the end of that day. So if there was 6 technicians at each pump truck, that means in 13 hours, you probably would have made, I don't know, a dozen sets of concrete, maybe making a set every half hour. That's a lot of work. Anyway, fun projects, they're big. There's a lot of steel involved. This is actually inside the MAP foundation, looking out from Oakland Construction's website of that concrete pour. This is a massive amount of steel. So you can see in that steel class that you guys are all taking right now, you can see, maybe you can tell what kind of rebar this is. You kind of see the stamp up there. It's like, 8, that's an 8 bar, it's like 1 inch diameter, big bar. Impressive. MAP foundations are strong. It's what you do when you're doing when you've got good soil to build on. But we need to talk about what's the bearing capacity of these. But before we go into calculating it, and you're going to like how to calculate the bearing capacity of MAP foundation. It's not too crazy. I just want you to tell me what are some reasons why. Why would you choose a MAP foundation? And we're not going to have multiple choice questions, but what do you guys think? What are some reasons from the reading or just intuition? What are you thinking? When would you do it? Why would you do it? What are some thoughts?
You gotta distribute the load of the building over a really large area.
Yeah.
It's not just one specific spot where a foundation, that's the entire area.
Okay, so there's a lot of column loads coming down. Yeah.
Would you want it for like soil that's just not as strong?
Yeah, that's right. You got to spread it out. If you had designed a bunch of small footings, but you were finding that because the soil is so weak, you've had to make the footings not just 5 feet by 5 feet, but 10 feet by 10 feet. And now one column footing is being butted up against the second column footing, and you're ended up just designing a mat foundation anyway when you originally were just trying to do spot footings individually. Yeah, because the soil is weak. What else? What are other thoughts? Observations from some of these pictures that you saw. What are some unique things that you're seeing in this picture right here? Like how close is this pour to the neighboring structures right here? Look how tight this is, these tight quarters. I mean, there's big buildings all around here. You know, when you have a footing that comes down, a normal footing, you design it like this, right? So if you have to have a column that comes down, you want a footing like this. But what if this is the property line right here? What if that's the wall and your neighbor's already taken this? You can't build a footing that looks like that. It just doesn't work. And so what you have to do is then just create this giant mat foundation. And so amount of real estate that you have would be a reason. As mentioned, the soil has low bearing capacity, has to be distributed over a large area. If you're designing all these spot footings and you're finding that you cover up 50% of the area anyway, well, why not just go and do a mat foundation?
Is that because you would save on labor?
Yeah, it just make it easier. Yeah, and maybe you would have to make each footing so beefy and thick. Maybe you can thin the mat out a little bit and just spread it over a whole big area. Yeah, so you'd save money in the end. This is what I was talking about. The walls are so close. The side of the building, the stress on the soil needs to be reduced. Differential settlement. If you have a bunch of single footings over this big area, you do run the risk of a site that has different soil conditions from one end to the other. Maybe this footing will settle 1/2 inch, this footing will settle 1 inch. You don't want to start having all these little possible cracks and one footing settling more than, if you just had one big mat, then boom, it would kind of bridge over any of these soft spots, right? This is kind of the same thing when the soil strata is unpredictable and there's pockets of compressible soil. Go ahead and use a mat that will bridge over anything. In Florida, they have a lot of karst topography where water could go in and carve out little caves and stuff under the ground. So if that could be your possibility, use a mat foundation. Because if you just had like 5 or 6 footings, what if one of those footings was over a cavern or something like that? Whereas if you had a mat foundation, it could bridge and handle maybe a little area that's softer or something like that. Or if you do a basement, that's a good idea as well. I'll save these videos for later. They're just on how to compact ground. If we have time, we'll get to that. Okay, so let's talk about for situations where a single foundation may extend beyond the property lines, how would you even design it? When I just said, normally you have a footing that would come down and just be a nice square footing, circular footing, rectangular footing. Great. Well, what if the property line's right here? How do we even design a foundation like this right here? We have some property lines. Normally you have your footing that would extend this way, but you can't now. Well, kind of the method is first you got to figure out where the 2 loads coming down. So Q1 and Q2, that's the big load that's coming down from your columns. And so the area of footing that you're going to need to support that would be equivalent to what is the net of how much first can your soil handle? What's the net allowable? It's like 2,000 pounds per square foot. What is it? And divide it by your total load, then you'll know the area. And then to figure out some total lengths, you can go ahead and just start kind of following a little process to calculate the length in between the 2 footings, the width. And mat foundations, they kind of have this method that you can follow. It's not too crazy, but you just slowly go through the steps to kind of design the first 2. Now, a mat foundation normally has lots of columns that come down on it. And you don't just have to do rectangles. You can do trapezoidal areas. You can determine, there's many different shapes. Maybe this side of the structure that you have is a lot heavier than this side or something like that. Anyway, there's an approach to kind of figure out the total area that you would need. And again, if the area ends up being, if you're just doing little footings anyway, and it's over 50%, then you can start to go into this approach to see kind of shape, kind of area would you need to hold up your foundation, right? And of course, in the end, if your loads are so immense maybe a mat foundation won't work, right? A mat foundation works if the loads that you have divided by the bearing capacity of the soil can fit in an area of property that you have available to you. But there are conditions where the building's so big that the area that you would need is bigger than you have the real estate for. So mat footings are maybe a middle step towards a deep foundation, right? We've been talking about shallow foundations. Mat foundations would be the next level. If your mat foundation, the area still wouldn't be enough area to handle these loads, these Q1, these Q2, all the loads. I mean, there's Q4, 5, 6, 7, 8. This is just showing 2 loads. But you may have a situation where the area is just not big enough to hold this load. And so that's when we're going to get into deep foundations. But just know that mat foundations kind of are the middle ground. And there's ways to figure out how much area you're going to need. And normally you have enough area, but the buildings just keep getting bigger and bigger. And there's at some point you'll run out and you'll know, okay, mat foundation is not for us. Now there's different kinds of mat foundations. Maybe you've seen some before on construction sites. The book just kind of goes through a couple different variations. And really the main variation is this one will just be like a very flat surface on the ground. Here you can deepen wherever you have a column on it. You can kind of widen them a little bit more. You could put a basement in there, have some big walls or something in there. There's just many different kinds of mat foundations. Actually in Texas, mat foundations, there's like a hybrid version. I wouldn't really call it a mat foundation, but it looks something like this middle section B right here, a flat plate thickened under the columns. Homes in Texas are all built on clay. And so what the contractors typically do, they want to pour the home on a big concrete pad, right? But what they do is they dig deep trenches kind of on a grid pattern. The trenches go down maybe 3 feet. And so what you'd have looking at the side of it would look kind of like section B. You'd have your 3 or 4 inch slab that covers the whole foundation of the house, but then you'd have these little nubs that come out down 3 feet. And what they actually do, they run these hollow tubes, these hollow plastic tubes down the length from one end of the house to the other in a grid pattern. So running north to south and east to west. They pour the concrete slab and then they come back after the concrete's hardened and they post tension. Those hollow tubes, they can run a cable inside of them. And so the cable has never been embedded in the concrete. And then you can come and you can tension, you can pull on those really tight. And then you could put lock nuts on there. And so it lock that tension in. And so every cable is now squeezing together in this grid pattern. And it's squeezing that big concrete mat that has those trenches. And each one of those trenches is where the cable runs to make it a little bit stronger. And so houses in Texas on clay are built this way. And it creates a raft, right? Because clay can cause differential settlement. You know, you leave your sprinklers on one night more than the other side of the house. And now your house is doing all kinds of stuff. So what they do, they essentially squeeze that concrete together and create a raft or a mat foundation that can handle the loose soils and you don't get as much cracking. Otherwise, you get your house is cracked like crazy. They actually recommend to people in Texas to water their lawns year round, even though the grass doesn't grow for half the year. It's just they don't want the soil to dry out in the winter, shrink, desiccate, and then swell in the summer when it rains again. That shrink swell action causes tremendous loads. Just like that picture that we saw, that guy was able to lift his whole car just using the pressure from his exhaust. That's not a lot of pressure. That's like the amount, just like pushing with your one finger. But imagine clay has like millions of little fingers all pushing up with 1 pound and your house is getting lifted and cracking, things like that. So anyway, there's lots of different mat foundations. But our main question is, okay, so I figured out the area that I need to hold up my soil. How much can it hold? So we're going to go back to the general bearing capacity equation. These are the exact same slides resurrected from chapter 3. Terzaghi's equation is here again. And you may be familiar with hunting these things down. We'll have an exam question. I think we'll use something like this. So we're going to have to be familiar with this. So this is good practice again. We're going to have to be familiar with this table, right? For every one of those factors, there's a way to figure it out, depending on which conditions you have. If your depth of your soil divided by the width of your footing is less than 1, or if it's greater than 1, there's all these different relationships. We need to understand them because for mat bearing capacity equations, we use the general bearing capacity equation that we just showed. And how you figure that out is you have to subtract the soil above it, right? The soil can hold a certain amount, right? That's some bearing capacity. So if the soil can hold a certain amount, you just put your big mat foundation on it. Normally you don't put your mat foundation right there. Normally what you do is you bury your mat foundation a certain depth down under the ground. You dig a hole, put your mat foundation in, and then you build up from there. So what we're saying with this equation right here is that the Q net U, that's the ultimate net bearing capacity, is equal to QU minus Q. Now we got 3 different Q's up there. What do they all mean? So the little q at the very end, the QU minus Q, that minus Q, that's this little value right here. That's how deep it can go down times the unit weight of the soil, right? Because the soil right here, it can hold the building on it, but then it's going to either be buried with other stuff. You just have to subtract out the soil that was on top of it. That's what that little q is. And then this is Terzagh's general bearing capacity equation. So this is how you figure out not your gross ultimate bearing capacity on mat foundations. If you have granular soils, you use this equation. If you have saturated clays, you use this one. And you may be saying, oh, I don't remember those. Those look familiar. Those are just this. It's this same equation right here, but one of them cohesion is 0, right, in sand. The other one, the friction angle is 0, so this cancels out. And then all these little factors, they just grab the shape factors and everything from right here. See how this got a little 1 plus B over L, and they just put them in already. So they've kind of done the work for you, so you don't have to hunt them down. So gross ultimate bearing capacity for mat foundations in saturated clay, where phi is equal to 0, you use this equation. And these numbers are
QU is the stress that the foundation puts on the soil. Is that what QU is?
Yes. This is your load. Yeah. Subtract out the amount of weight of your existing material, leaves you with the net allowable that you can then put in there. Your ground can handle this much, so you can only put this much on it. Okay, so there's 2 new equations right here. Then, if B gets a little bit larger and you want to use N values, you can do that as well. So notice this one's for SI units. This one's for US customary units. So there's just 2 equations. And if you know settlement, you can put this in here and calculate net. Now, maybe you don't know settlement. What would you pick? You would have to choose your own settlement in millimeters. What's the maximum amount of settlement you allow on this building? You put that in there. Notice that if you put in 25 millimeters, that just goes to 1. So 1 is actually what I put in. I'd say settlement of 1 inch is a common. So what would you pick? Pick whatever you want. I would never go more than 3 inches. And the book has some good recommendations. And I think as you go through here, it has some, based on observations, some recommendations on kind of how to reel you in as a geotechnical engineer on what you should pick and what you shouldn't pick. Can't remember what page it's on, but I thought it was in here. So let's just try an example. Just there's 2 examples I want to go real quick and then we'll wrap up. But that's it. So there's just those 2 equations for today. So determine the net ultimate bearing capacity of a mat foundation, 12 meters by 10 meters, that's big, on a saturated clay. So there's no friction, so we just have cohesion. CU of 105, no phi, friction angle 0, and we're burying it 2.5 meters under the ground. So we would grab that equation that was just on the previous page, value, this is the equation right here, and then we just start plugging in all the stuff that we know. We know CU, that was given to us. This value that comes from the table pre-filled in for us. All we really have to put in our base and our length values right here. And then over here again, how deep are you going and what's the base? So pretty basic equation, again, derived from Terzaghi, and it helps you calculate Band capacity, what that value is, right? Any questions on this example? I feel like these. Let's look at one more. Determine again the net ultimate bearing capacity of a mat foundation, same size. This time it's not on clay, it's on sand that has blow counts of 12. And you're saying the allowable settlement is 20 millimeters. And that is one thing you have to recommend as an engineer. What is the allowable settlement? And I'll let you choose that. In this case, they're saying just less than an inch. And so again, if you're presented with blow counts, the main things that we need is how deep are you going to bury it, or FD, not DF. You have to be careful on that. What's FD again? Does anyone remember what FD is? Not to be confused with DF. FD. What is FD? How do you figure that out?
We use that. I know we used it on the
We
last
used it before on the last one. Who remembers what it is?
depth factor. Yeah, it's unitless, right?
What's that?
It's unitless, right?
It's unitless. How do we calculate it again? I don't have it on here. What's that?
Yeah.
It's
The 1 plus 0.33.
It's this guy right here. Okay,
Yeah.
one. Okay, yeah. Okay, so that, yes, it is here. FD is 1 plus 0.33, and then it's your depth divided by the width of your foundation. Okay, perfect. So just be careful that whenever you see that, you recognize that's what. Okay, so then this one will just spit out 129 kilonewtons. So really, two new equations. One equation is if you're given blow counts and you're going to control by settlement. Because we know most foundations, they're going to either fail with bearing capacity or settlement. And so if settlement's going to control, then let's just put 1 in here. We won't even have to calculate settlement. We'll just hold it at 1, and then that's what the soil will be allowed to hold if it's that stiff. Blow count of 12. This mat foundation I find is a lot less tricky. There's no tables that you need to use, things like that. Generally, shallow foundations are designed for a mat. What do you usually put in there? You used to have 20 millimeters, 1 inch. What would you know with it? Here's a quick. I just want you guys to respond. Go into iClicker. Generally, what would you pick? 1/4 inch, 1/2 inch, 3/4 inch, 1 inch, 1.5. You can't choose anything you want, right? But what's generally, what do you put? I've probably said it many times. I said it today. What would you put in there? Let's kind of know what you guys are thinking. Okay, good job. Okay, D1 inch. That's what I thought I'd do. And 1/4 inch, that's rare. Now, why is that a big deal? Why would you, what if you said, hey, I'm an engineer and my foundation is going to be designed for a maximum settlement of 1/4 inch. What are you telling the client right there? I guess what's the difference? Why would you
have a lot more? You're going to pay a lot more for it. Right? So you're trying to get more compaction in the soil or a lot more for the foundation.
That's right. If you suggest these very little tolerances right here, it's saying you're being so conservative, they're going to have massive foundations so they don't get any more than 1/4 inch. But if you say your design calculations were based on the fact that you're okay with 1 inch of settlement, then it allows you to shrink up those footings a little bit. I mean, yeah, you can get a little bit of settlement, and most buildings, that settlement happens at the very beginning, and so it's safe, right? 1 inch is safe. If you say you can handle up to 1.5, that's okay. I would never go above 3 inches. I've never personally said anything. I mean, 1.5 is probably the most I've ever said. And it was a site, after I looked at all the end values, I ran it in the spreadsheet and it was giving me some high values. And I was just kind of playing around like, okay, well, what if I took out 2 feet of soil underneath the foundation? And that's what you do as an engineer. You just play with your spreadsheets and just try to, you don't want to recommend crazy values. You want to try to stay around here. And so you just try to optimize. And the goal, if you have a weak soil, you either build a big pad of dirt on top of it to spread the load out, right? Because dirt is cheaper than a concrete footing, right? Footings, a big 10-foot footing, that spreads the load out. But cheaper than a footing is a gravel pad, 1-2 foot gravel pad. So if I ever have a soft site, before I would recommend a footing, with 1 inch settlement, I would say, well, maybe what I could do is I could recommend putting a foot of fill across the site, and then I can increase my bearing capacity, right? If the clay can only handle 1,500 pounds per square foot, well, why don't I recommend maybe 2,000 or 2,500 pounds per square foot with a 1 foot of gravel on it? So that, and then we just let the designers take it from there. As geotechnical engineers, you don't have to give them all the answers. You just give them some general guidelines. Okay, maximum settlement. What about differential settlement? What would you do? Last question. Differential settlement. What would you say there? We haven't talked too much about differential settlement, but you can imagine you build a building, you get some differential settlement. If you're going to make some recommendations, generally, your foundation is designed for what? There's been no really equations about differential. There's some sections in the reading that talk about differential settlement, but we're not getting in there. But I'm just curious what you would put. Okay, let's see. B, 1/2 inch. Okay. And I think that's appropriate. I wouldn't put 1 inch. I wouldn't put 1.5 inches. I mean, differential sediment, that's saying you have a big foundation and one side of your foundation can move by up to 1.5 inches. By the time concrete does that, it's starting to crack. But concrete can handle B, 1/2 inch, 1/4 inch. I even recommend say that sometimes. So, and we got in this ballpark. There's nothing wrong, but B is the most probably recommended value right there. Okay, so your homework is going to be pretty straightforward. 1, 2, and 3 from the book. I don't think there's any errors in these 3 assignments right here. So you'll just use those 2 equations. It's either US units or SI units. Pretty straightforward. Then Wednesday, we're going to talk about lateral pressures. And then Friday is our exam. So that's kind of where we're headed this week. So turn in your homework tonight by midnight, and we'll just keep plodding along. Thanks, everybody.
We can review anything on Wednesday.
We may review a little bit on Wednesday, and we may still trying to decide if we want to have Friday be a review day and take the test home. Still trying to decide. And once you get the test over with in 60 minutes, I mean, it's not meant to be tricky, so we can just do it in class. We're going to take it home. You still have a time limit where you take it home. Yes.
Yeah. I just wanted to. Yeah. So I just checked the problem. So I was using PDF until I got it. Because I checked my book and I'm like, no, it's the same. But his PDF was more one unit, like one, like the meter.
Yeah, because your pictures were the same.
Yeah.
It's just different numbers.
This is the thing is that I actually like would, I know the key, right? So I would use the same numbers and then change it to like just to check if it would be the same, and it was the same. So, but yeah, thanks though for I gotta go finish with the concrete and start
Yeah, so then there's a Q right here. Yeah, and that there's the Q by itself.
So now does that mean for this one?
And then there's Q.
Oh, there we go. And I already have this one. So I can have this one. This is but I need to find the Q next. This is not able to.
No, the questions have always been asked. I can look at this. Well, at least all the keys that I have are and there might be some changes, but I can look at the keys. Okay, no. There were 6. Yeah. I didn't know. Okay, so I'm not. Yeah. All thinking of.
Number 9. Yeah, I don't know how to explain it.